Hey, Linford here, and today we're going to be talking about relations in mathematics. We're going to go and specifically define what a relation is in terms of set theory, and then we're going to define range and domain of different relations and try to figure out if we can come up with a way of visually determining what the domain and range of a particular set is. Now, first we're going to go ahead and define a relation. Now, in mathematics, a relation is a set of ordered pairs, x, y. And it's pretty simple. It's really just a set of ordered pairs. So you have a collection of ordered pairs or coordinate points. For example, if we made a quick demonstration, let's take this set 1, 2, 3, 4, 5, 6, and 7, 8. I don't know. There. 4 coordinate points. Cool. I have a set of ordered pairs. Heck, I could even have a set of 1 ordered pair. There we go. Okay. A relation really is the introduction to how we're going to start exploring how x and y are connected to each other. Now that really gets us more in depth into talking about domain and range. The domain is the set of all first components in the ordered pairs. And by that I mean the set of all x's. So in an ordered pair, we have, I'll try to do this in a different color, we have x and we have y. So the domain is the set of all of the x's, pretty much. Now, we don't always have just x and y in ordered pairs, but in an algebra class like this, that's all we're going to be looking at. So we're going to be looking at x and y values. So the domain is really the set of all x's that you're going to have in all of the ordered pairs. Similarly, the range is the set of all second components in the ordered pairs. And for our class, that basically just means the set of all y's. So while the domain was a set of all x's, the range is going to be the set of all y values. And this is kind of how we're first going to start looking at what the connection is between all of the x's and all of the y's. So if we start connecting domain and range, when we work with relations, we're really going to be looking at it in a very basic sense. We're kind of just going to be more so looking at each thing one by one. So let's define the domain and the range of this set. Okay, clearly I have a relation because I have a set of 1, 2, 3 ordered pairs. So let me take all of the x values that I see here, 1, 3, and 5. And let me take all of the y values I see, 2, 4, and 6. This is what's called a correspondence diagram. So this is a correspondence diagram, and what it really shows, we oftentimes draw arrows between the domain and range, and what we're trying to do is show visually how each x value is linked up with each y value. And we're going to look at this even more when we get to functions and try to see how what we call mapping, how all of the x values are mapped to y values. But for right now, we're just kind of seeing how certain things are linked up and trying to get a sense of what domain and what range are. So let's take an example here, y equals x plus 1. We want to figure out what is the domain and what is the range of this equation. Now first off, we should realize that we are in fact working with a relation here, because we can say that equations, I abbreviate that EQS, equations are relations. And that's really because, remember, an equation has infinitely many points, okay? This equation, y equals x plus 1, that represents a relationship between x and y. It says you're going to have very specific x and y points that are solutions for this, and those are the ones we want to look at. So what is the domain and range here? Now, here's where the trouble comes in. This is a linear equation in two variables. There's infinitely many solutions to this. Like, for example, if we just start picking some out, x could be 3 and y could be 4. X could be 5 and y could be 6. If x is 10, y is 11. There's infinitely many points, and there's even decimal points I would have here, and fraction points and square root points. So we're really kind of at a loss because we can't really do a correspondence diagram like we did before. Instead, we need to think of interval notation. Now, one of the best ways to figure out the domain and range and writing it in interval notation, because again, we have infinitely many points, so really our only hope is to write something as an interval. What I like to do is always have a graph down. Let's go ahead and graph this equation. X plus 1. Let's pretend that the intercept here is 1, and let's just try to graph this line. Let's just pretend that's pretty much what it would look like. Now, let's think, what is the domain of this? And remember, domain is the set of all x values. How could I go about describing the x values that I'm seeing here? All of these individual x points and the coordinate points that they produce. Take a minute, pause the video, and see if you can think, what is the domain of this particular equation? All right, well, hopefully you're able to think about it and kind of come up with some reasoning. But really, the domain of this seems to look at every x value that I might have as a coordinate point. But the trouble is, every coordinate point I have, there's an x value for every coordinate point, yes, but more specifically, I have a coordinate point, or I have an x value for every coordinate point. Did I say that right? Every x value for a coordinate point, and every coordinate point for whatever. Hopefully you get the idea. But basically what we're saying here is I could pick any random x value that I wanted, and I'm going to, at some point in time, cross the graph. For every x value, I will have a y value. And if we just look at this equation, am I prevented from plugging anything in for x? Is there any issue I have? Could I plug in 10 billion and 2, or could I plug in 500 trillion.1, whatever? I could plug in pretty much anything I want for x. So it doesn't matter necessarily, so we're going to say that the domain for this is negative infinity to infinity. We can plug in whatever we want, really, and there will always be a coordinate point for every single x value. Now, if we're taking a look at the range, maybe I'll do that in a different color. If we're taking a look at the range here, we just have to switch directions. That's the y values. So if I picked a random y value, you'll notice that any y value I pick, there will always be a coordinate point for that y value. And you should ask yourself, okay, is there any number I can't get for y? Is there anything like any number, and you could try this for an example, but is there any number that I can't get by adding 1 to a different number? And really you should say, well, no, I could have whatever I want for y, because I just have to find, if I took y minus 1 equals x, I could always find an x and y that will work. So really, what we're seeing here is that the range of this particular relation is going to be negative infinity to infinity. No matter what random y value I pick, I'll always end up crossing the graph at some point in time. Hopefully you're starting to get the hang of this domain and range stuff and see how really visually or graphically how we represent these sets and how we can interpret what the set of all the x's and y's are. Okay, let's try some practice problems. After each of these practice problems pop up, I'd like you to maybe take a couple minutes, pause the video, and see if you can determine what the domain and range are of these particular relations. All right, let's dive right into this first one here. We have a sideways parabola. Again, forgive my rather poor drawing skills. I'm working as best I can with the stylus. But we have a sideways parabola here, and it's supposed to cross at 0, 0, but close enough. Let's try to figure out what the domain is for this situation. Well, keep in mind the domain is what x values can you plug in and get coordinate points for. So where do you see coordinate points? Well, it seems like any x value I pick will give me a coordinate point, and even at 0, 0, right, there's a coordinate point right there. But wait a minute, if I go out on this side, I'm in the negatives, I don't see any coordinate point over here. The graph never comes over to the negative side, it only goes on this positive side. So I'm going to say that the domain of this relation, well, it goes from 0, that's the lowest it can be, and then it just keeps going on forever and ever and ever in the positive direction. I can always keep picking x values, and eventually I'll cross the graph. So I'm going to say from 0 to positive infinity, and I'm going to include 0. I'm going to put a bracket on that, because again, if I plug in 0, I get 0. There's a coordinate point right there. Okay, now let's talk about the range. Let's change up colors a bit here. Now the range, any y value I pick, seems to always give me a coordinate point. And that's true, because this graph, really, sometimes people think they kind of level off. They don't, actually. They're going to keep going on forever and ever. They're going to keep decreasing, and they're always going to keep increasing. They might, increase slowly or decrease slowly, but they'll keep going. So really, the range is negative infinity to infinity. Because for every y value, there will always be a coordinate point. I can always link it up with an x value. So a big idea that we're seeing here that we might want to note to ourselves is the domain, and I might kind of go back a couple here. The domain is how far left and right the graph goes. And the range is how far up and down the graph goes. That's really what we're seeing here with domain and range. This is a good visual way of representing the two. All right, now we have a situation where I actually don't have infinitely many points. We only have 4 individual points. Let's see if we can figure out how to go ahead and write the domain and range of this set. Sometimes people will take this and they get so used to writing interval notation, because let's be honest, I would say like about 99% of the time, anytime you work with a relation, you typically are going to write the domain and range in interval notation, right? We have graphs, we have equations that model this stuff. This is a situation where I just have 4 individual points. This is called discrete information, because we just have individual points. We don't have continuous information. So I'm not going to go and write this in interval notation, okay? Because these are just 4 points. I don't have an interval. Remember, an interval means you have infinitely many points, and we're trying to say everything between 2 points. No, here I'm just going to list all of the information. So for the domain, we'll say all of the x values are -3, 1, and 3. These are all of the x values that are used in the domain. So please make a little note to yourself that it is not going to be -3 to 3 in brackets, okay? This is not the case. We are not using interval notation here. Another thing that people might realize is, wait a minute, Linford, wait a minute. We had 4 points. There is a 1 right here and a 1 right here. but you only listed it once. That's because we actually don't double list points. So we're not going to go and double list points that were, or individual elements, I guess I should say. So go ahead and just write the one only one time. So let's take a look at the range then. Let's make a set of all y values. So I'm seeing here -4, I see 2, and a 4. That's a terrible brace. Okay. And again, you might notice, wait a minute, Linford, we have a 4 right here, and we have a 4 right here, but you only listed it once. Again, we don't double list elements. Don't worry about that. Just write each thing only once. And here's our domain and range. Pretty simple. The big thing to realize is that we're not using interval notation. We're just listing what the individual elements are. Okay, this is my terrible excuse of an ellipse. Imagine it was drawn much better. But for the most part, this is supposed to be an ellipse. The lowest it goes is -2. The highest it goes is +2. The farthest to the right it goes is 4. And the farthest to the left it goes is -4. So pretend like it was drawn perfectly. So let's take a look and try to figure out what the domain and range is of this particular graph. Okay. If I was looking at the domain of this, again, I'm trying to find, if I pick an x value, will it give me a coordinate point? Well, this x value does, and it looks like this x value does. Okay. And even the point when x is 4 or -4, I get a coordinate point there. But as soon as I come over here, I no longer have a point. So it seems to me that my graph represents that my domain is -4 to 4. And I'm going to include those endpoints, because everything between -4 and 4, everything in between those two numbers will give me a coordinate point. And really, you can see this by asking yourself, how far left does my graph go? Well, it goes as far as -4. And how far right does it go? Well, it goes all the way to +4. So there you go. That's the domain. That's really what it visually is representing. Then the same thing with the range. We're trying to figure out how far high and how far low it goes. So if I pick a random y value, does it give me a coordinate point? And really, as long as I stay in this graph, it kind of does. But as soon as I step outside of the graph, there's no longer a point where it crosses. So what we're going to say is that the range for this particular ellipse is from -2 to 2. And I'm going to include those points. And really, we can see that by saying, how far low does the graph go? Well, it goes down to -2. How far high does the graph go? Well, it goes up to +2. And that's it. That's really all that we're saying here when we find the domain and range. Try to use this idea with the next one. Okay, again, actually, I guess this one isn't that bad of a drawing. This is supposed to represent a parabola. Again, just try to go with it. Now, this is a parabola, but you'll notice that the parabola stops right here. It stops at the point 4, -2. That's this point right here. And the open circle means not included. That means the graph gets, as we come along on this side of the graph, we are going to get incredibly close to this point without actually hitting that point. That open circle means that the function is not defined there, okay? That point, it's an open circle. It's not a part of the relation. So 4, -2 is not a part of the relation. That coordinate point is not included in the relation. Hopefully I've said that enough for you to realize. So let's talk about what's the domain of this and what's the range of this. Maybe it's a little easier to start with the range. Okay. This side of the graph, it's going to keep increasing. Well, maybe it kind of looks like it's tapering off, but it really doesn't. This is a sideways parabola. It's going to keep increasing the farther and farther we go out. So with that in mind, I know that the height of my graph, well, I'm going to be going off to -infinity. Or I'm sorry, positive infinity. I'm mixing up my infinities. So I know I'm going to go up to positive infinity, but how far low does the graph go? Well, it seems like the graph stops here at -2. If I was at, for example, -1.99, well, I'd have a point on the graph, but as soon as I get to 2, I don't have a point. So it seems like my graph starts at -2, I'm not including -2, and goes up to infinity. Hopefully that should be pretty obvious. How far low does it go? Well, -2, and then it keeps going up to infinity. Now let's take a look at the domain. This one's a little trickier, but not too bad. I think it's pretty obvious that our domain starts at 0. Right? There's a point right here. How far left does the graph go? Well, 0. Nothing over here is going to give me a coordinate point. So we start at 0, and then we have to ask ourselves, how far over do we go? A lot of times, students say, well, we're going off to infinity, but what about this point 4? What about this weird open circle here? They kind of want to not include the point 4 because they say, well, Linford, look, if I plug in the point 4, I get a hole in the graph. And I always tell students, hey, keep drawing your line. And they realize, oh, wait a minute. If I plug in the point 4, there's no solution right here, but there is a solution there. So we're going to say the domain goes from 0 to positive infinity because, again, the domain is what x values have been used. And basically, the domain's saying, has 4 ever been included as an x value? Of all the coordinate points you have, of all these infinitely many coordinate points that you have, is 4 ever listed as an x value? And we can say, yes, it is, because there's a solution right up here. There's a coordinate point right there. Now, some of these points, like for example 2, some of them have 2 coordinate points that match up with that. But 4 is one of them that has only 1. Same thing with 5. That only has 1 coordinate point. So we don't need to worry about that. We don't need to worry about 4. We're going to include it. So really, we're going to say the domain goes from 0 to infinity. All of these x values have at least 1 coordinate point they're matched up with. All right, well, hopefully this video has made sense. Hopefully we've been able to define what a relation is, define domain and range, and have some rather visual techniques for figuring out what the domain and range of different graphs, different equations, and different relations are. If you have any questions, please let me know. My email is Linford, Linford, at wccnet.edu. Let me know if you have any questions or comments. I'd love to hear your feedback. And until next time, take care.